Everyone, we're going to present you an interesting and fun war story of Professor Steven Skeena. This presentation is done and created by Life Fellows Lian Zana and Enes Garval. This war story is called String 'em Up. So, we first begin by exploring how this story started. Professor Skeena's interest in algorithms expanded also in the field of biology, where he could find an interesting intersection even there, specifically in the field of bioinformatics. Inside the genes of humans is encoded all the information that is required to build a human, and by sequencing the human genome, we've had great impact on medicine and molecular biology. Therefore, the professor was interested in this field for these reasons. The DNA sequences can be precisely represented by using strings of characters with the four letters A, C, T, and G. And biologists' need for string matching and shortest common superstring recently has caused algorithms to become interested in solving these old algorithmic problems. These DNA sequences can be very long strings. For instance, the human genome is nearly 3 billion base pairs or characters long. Therefore, using asymptotic big O complexity analysis on this large problem size is rightly needed. And also, sufficient amounts of money are being invested in genomics for computer scientists for their contribution. The proposed technique for DNA sequencing, which is called sequencing by hybridization, piqued an interest at Professor Skeena. This technique attaches a set of probes to an array, thus forming a sequencing chip. And these probes determine whether or not the probe string is a substring of the target. By finding which strings are and are not substrings of the target DNA, the scientists could sequence the DNA target. The example which they took was the supposed AC, CA, and CC as the length 2 times K substrings of S. And they said that ACCA is a substring of S, since the standard substring CC is one of their possibilities. But CAAC was not, since they didn't have AA as a substring of S. As shown in the figure, the 9 possible concatenations of AC, CA, and CC are as shown in the text below. CAAC is not considered since AA at the center of the string is not present as a substring of S. As algorithmic scientists, they looked upon which dictionary data structure is fastest to give us the acceptable K strings. They needed to find the fast way to determine whether the K-1 substrings spanning the concatenation were members of our dictionary of permissible K-strings. By using a binary search tree, finding the correct string would take big O of log n comparisons, where each comparison tests which of the 2 length of K-strings appeared first in alphabetical order. This would take a time of big O of K log n. This idea seemed good, and that's what Skeena's graduate student, Dimitris Margaritis, thought. But things weren't as expected. Dimitris complained, "I've tried the fastest computer we have, but our program is too slow. It takes forever on string lengths of only 2000 characters. We will never get up to n equal to 5000 characters." The problem on this, as they found out, was that all the time was spent searching in the data structure. That is because they did K-1 searches for each of the ON squared possible concatenations. So, Skeena proposed using a hash table. He told them that it would take O K time to hash a K character string and look it up in the table. That would take a factor of O log n. However, Dimitris still complained. This time, the program could reach 10 times faster on strings of length 2000, but they were still taking a lot of time to reach 4000 characters, let alone 50,000 characters. The reason for this is that when we look at k character string, we must read all k characters, and that does all k searching on our hash table. Considering that, for example, when we concatenate A, B, C, D with E, F, G, H, we are first testing whether B, C, D, E is in the dictionary than C, D, E, F. These strings differ from each other by only one character, and they thought that each subsequent test should take constant time to perform, not OK. A binary search tree won't help either, since the keys ABCD and BCDE differ according to the first character. The two strings will be in different parts of the tree, Dimitri's observed. However, Skeena came up with a solution for this. He told him that a suffix tree would help to do this, since a suffix tree would contain all the suffixes of a given set of strings. The suffixes of ACAC are ACAC, CAC, AC, and C. In join with the suffixes of string CACT, we get the suffix tree at the figure shown. By following a pointer from ACAC at the green node to the longest proper suffix CAC, we can properly test whether CACT is in our set of strings just by doing one character comparison there. However, this program, albeit it is faster, it ran out of memory. That was due to the suffix tree building a path of length of k for each suffix of length k, which made it become O(n) squared nodes in the tree. So when reaching 2000 characters, that makes it crash, let alone 50,000 characters. Skeena still didn't give up. He stated that by using compressed suffix trees, we don't have to explicitly represent long paths of character nodes. We can refer to the original string and they take a linear space always. Now, finally, Dimitris got the result he wanted. The algorithm worked fine with a simulation of strings at n 65,536 without issues. And most importantly, the lessons from this story were taken. By taking a single operation, which was a dictionary string search, and testing it over again, they found the right data structure to support it. Looking deeper at the kind of queries being performed to find a better data structure helped them make the dictionary structure efficient. However, this could not be achieved without the persistence at looking deeper at the problem until finding the right solution. This was a project for our Data Structure and Algorithms class, instructed by Professor Irjan Chanhasi. We really hope you enjoyed our presentation. Thank you for your attention.